Welcome to the course analysis of several variable, and today we are going to start the module 5 where we are going to discuss few main theorem of differential calculus with function of many variables. So in this regard, our first theorem is multivariable mean value theorem, which is section 5.1. So before going to state the mean value theorem, we recall about the following definition. So this says that if AB are 2 points in Rn, then we define the interval, closed interval AB on Rn is a parametric form x equal xt equal A plus t b minus A, where t is from 0 to 1 and this subset of Rn. So this is the interval of A, B. So this we define in the Rn. Now if you see that in this case, if you take t equals 0 and if you put it here, you will get A, which is the initial point A. And if you take t equal 1, then you will get A plus B minus A, so which will gives you P, so the endpoint. Now we have the statement of the mean value theorem. It says that let omega be open on Rn and f is a functions from omega to Rm and it is a differentiable function. Now if we take 2 points A and B in omega such that the closed interval AB belongs to omega, then for all V belongs to Rm, that is in the domain codomain set, there exists a C in the interval AB such that f of B minus f of A dot B is equal f dash C B minus A dot B. So this is the statement of the mean value. Now we are going to prove this theorem. Okay, to prove this theorem, so let V belongs to Rm and define a function g from close interval 0 1 to R close interval 0 1 to R such that gt is equal f of A plus t b minus A dot so we can note here that g1 is equal f of A plus B minus A dot V. So this is equal f of B minus V, and g of 0 is equal f of A dot V. So now the question is that we define this function. So is this function is well defined? The question is g is well defined on omega. So first we have to check it that it is defined in on omega. So now how we'll prove that one? Now for all B belongs to Rm and 0 less than equal t less than equal 1, A plus t b minus a is belongs to closed interval AB, which is subset of omega as given there. So this implies that since it is belongs to the closed interval and our given function is defined on the omega, so therefore f a plus t b minus a is defined and f a plus t b minus a is belongs to Rm because it is mapping from omega to Rm. So therefore, if the image of a plus tb minus a with f, the function f is belongs to Rm. So now, so what is g? Since g is since since gt is equal f of a plus t b minus a dot v, so this is both are belongs to Rm, is it is well defined. Okay. So now next is that we have to show that defensibility condition. Okay, so now the second part will start is here. So it is given that it is given that f is defensible. F is defensible. So since f is defensible, so defensibility implies continuity. F is continuous. So this implies G is continuous on the closed interval 0, 1 and defensible on open interval 0, 1. So now this is a single variable function. So we know that from the intermediate value theorem we have, so therefore there exists a T naught belongs to open interval 0, 1 such that G dash T naught is equal limit s tends to 0 G of T naught plus s minus G naught Gt naught over s exist, and we have here this is equal limit s tends to 0. So now we will change this g naught t naught z functions to the f function. So you will get it f of a plus this is t naught plus s over b minus a dot b minus f of So minus f of a plus t naught b minus a dot v, and then overall divided by s. So therefore this is equal. Now we are trying to find the limit. So now for the simplicity, so let's denote x naught is equal a plus t naught b minus a. So therefore we can rewrite it g dash t naught is equal limit s tends to 0 f of f of x naught plus s b minus a dot v minus f of x naught dot v. Okay, so over s. So this is, we can separate this limit. Limit s tends to 0. Since f is a dot product, so we can write it here. F of x naught plus s b minus a minus f of x naught over s dot v. Okay, so this is nothing but the directional derivative of the function f, and which we can write it as this is equal direction derivative along the vector b minus a of f of x naught, and then this is dot with the vector v. So here dba is the directional derivative, and we know that. So this can be written as f dash x naught dot v. So here d b minus f x naught is the directional derivative of f with along b minus a. And we know that the relation between directional derivative and the vector is related with the point is like this. So for example, if you have d b f of x, so this will be written as f dash x dot v. So in this case, the v is b minus a. So to avoid the confusion, this is u, this is u. So therefore, du fx is equal f dash x u. So in this case, u is equal b minus a. So therefore, we can write it here f dash x, f dash x. Then we write this one as f dash x naught b minus a dot b. Okay, so now from our now we replace back x naught. So finally we'll get it. So therefore we get it. G dash T naught is equal. G dash T naught is F dash A plus T naught B minus A B minus A dot B. Okay, so now by it is also true that now we recall that there exists a theta belongs to 0 1 such that z1 minus z0 is equal g dash theta 1 minus 0. So this implies g1. So by the definitions of the g1, so what is function g1? G1 will be okay. So we know that here already g1 is equal fp minus v and g0 is equal fa dot v. So we substitute that value. So this will be f of b dot v minus f of a dot v. This is equal g dash theta. So from here we'll write it. So this is equal f dash a plus theta naught b minus a. Have this is v is equal f dash a plus theta naught b minus a f of b minus, and this we can take as a c naught. Now we have here our first consequence of the mean value theorem, and it says that if omega be open on Rn and f is omega is a differentiable function, AB belongs to omega such that this closed interval AB is in the omega, then f of b minus f of a less than equal absolute value of b minus a, supremum of f dash c for some c belongs to a b. And next corollary is that it can be more specific on that. So if this is differentiable and AB belongs to omega such that the interval omega, then there exists a C belongs to AB such that f of B minus f of A equal f dash C B minus A. Means we just can neglect the vector B with the dot product. So therefore, this is the another consequence of the mean value theorem. Next lecture we are going to discuss about the inversion theorem.